GameSci.com. GameSci.com.
Heidi ho! Welcome to Inheritance from Dictionary.com. In object-oriented programming, OOP, the ability to derive new classes from existing classes. A subclass inherits the variables and methods of the superclass and may, dare I say should, add new variables and methods. Let me just go ahead and say it. You should add new variables and methods when you are doing inheritance. What's a practical definition of inheritance? Never start with an empty editor window and type in all the code yourself. Find an existing class that does most of what you want and build on top of it. Is there a class that has 80% of the variables and methods you need? Build on top of it and you only have to write 20% of the code. That is code reuse. In other words, find something that's close to what you want and build on top of it. Here's a very non-computer example of inheritance. Let's say you want to build a tow truck. You could do it piece by piece. You could buy an engine, a transmission, a chassis, a tow harness, etc., and put all of those pieces together piece by piece. Or you could go down to the Ford dealer, buy a Ford F-350 pickup truck, which is 95% of what you need. Remove the bed of that truck, bolt on the tow harness, and bam, you've got a tow truck. You see what I mean by inheritance? If you start with a pickup truck, it's pretty easy to build a tow truck. If you try to do it piece by piece, it's much more difficult. So let's see how inheritance works with computer programming. Inheritance terms. The key to understanding inheritance is to understand the terms used to describe inheritance. The class in parentheses, enemy, says we want to create a new class out of an existing class. So vampire is inheriting everything enemy has. Zombie is inheriting from enemy. Mutant is inheriting from enemy. The following terms are used to describe the two classes. Some people call enemy the superclass and vampire the subclass. Some people call enemy the parent class and zombie the child class. And yet another set of people calls enemy the base class and mutant the derived class. Each term on the left is an existing class and each term on the right is the new class. These are the existing classes we are inheriting from. These are the new classes that are inheriting from the existing classes. Let's go through each example one by one. Here we have a class vampire that will inherit from enemy. In this example, class vampire is the new class that is created by inheriting from the existing class enemy. Vampire inherits the variables and methods of enemy. Vampire is known as the subclass and enemy is known as the superclass. Python and Java prefer using the terms superclass and subclass when describing the inheritance relationship. With Python and Java, it's pretty easy that you should learn these two terms because these two terms are used in the languages themselves. Class zombie inherits enemy. In this example, class zombie is the new class that is created by inheriting the existing class enemy. Zombie inherits the variables and methods of enemy. Zombie is known as the child class, and enemy is known as the parent class. I myself prefer using the terms parent and child class because they match the terms inheritance. A child inherits eye color or hair color from a parent. The terms parent and child match the word inheritance itself. Class mutant inherits everything from class enemy. In this example, mutant is the new class that is created by inheriting from the existing class enemy. Mutant inherits the variables and methods of enemy. Mutant is known as a derived class, and enemy is known as a base class. Some books do use the term base and derived class. The word derived means something created from something else. The word base means something you can build on. Mutant is derived from or based on class enemy. Terms. What are we going to do about all these different terms? Having three sets of terms to describe the new and existing class when doing inheritance is not ideal. But we have to live with it. Different programming languages, different textbooks, or online documentation use different terms, and we have to live with it. Just don't mix and match the terms. Never say the subclass was created from a parent class. Never say the derived class inherits from the superclass. Do not mix and match these terms. Try to keep them together. Now, why did it all happen this way? Because different professors who teach programming decided to use different terms. Professor A wrote a book and used parent and child class. Professor B wrote a book and used subclass and superclass. That's sort of the nature of technology. Different factions develop and they all like to use their own terminology. The problem with it is you go online, you start Googling inheritance, and one article talks about it this way, another article talks about it that way. We just got to learn to live with the different terms. Here is the meat of inheritance. When you build an object from a subclass vampire, it's going to have all the variables and methods from vampire, plus all the variables and methods from the superclass enemy. Vamp object equals vampire. That will create the vamp object reference to this vampire object, and you'll see inside the vampire object, of course it will have vampire variables and vampire methods. It's a vampire object. But it will also have the enemy variables and the enemy methods. Vampire inherits everything enemy has, so if there's a variable in the enemy class, vampire gets it. If there is a method in the enemy class, vampire gets it. Just like a child may inherit blonde hair from their mother and blue eyes from their father, the child class zombie inherits the variables and methods from the parent class enemy. Zom object equals zombie. We'll create this zom object reference variable, which points to a zombie object, and because it's a zombie object, of course it will have zombie variables and zombie methods. It's a zombie object, but zombie inherits everything that class enemy has. So it will also have enemy's variables and enemy's methods. That's what inheritance is. One day you may inherit a car and some cash from your grandparents. That's what inheritance is. When the derived class mutant inherits the base class enemy, it starts with all of enemy's variables and methods and adds its own variables and methods. This is what beginning students tend to forget. When you're doing inheritance, it's important for the new class to add its own variables and methods. You need to think of inheritance as something you add to, not just inherit from. The resulting object has both sets of variables and methods. Mut object equals mutant, or mut object equals mutant, however you want to pronounce it. I'm going to build a new mutant object. Mut object will point to that object. And of course it's a mutant object, so it'll have mutant variables and mutant methods. That's kind of a duh. But mutant inherits everything the class enemy has. So it will also have enemy variables and enemy methods. In object-oriented programming, OOP, the ability to derive new classes from existing classes, a subclass inherits the variables and methods of the superclass and may, dare I say should, add new variables and methods. Students often leave out that part about adding new variables and methods. Now why do we do this? Code reuse. We want to write the class once in enemy and use it in vampire, zombie, and mutant. When we inherit variables and methods from enemy, the classes vampire, zombie, and mutant can be shorter, more compact, and easier to write. Parent and child class design. Here is what we call an inheritance diagram. It shows that the classes soldier, drone, and tiger all inherit from a common parent class enemy. Class soldier inherits enemy. Class drone inherits enemy. Class tiger inherits enemy. What variables and methods go in class enemy? What variables and methods go in the child classes soldier, drone, and tiger? Good design leads to better code reuse. In this slide, we will look at designing classes with inheritance in mind. The class enemy. Common or shared elements in parent class enemy. What properties and methods do all enemies share? When you're designing class enemy, you should think, well, what does a soldier, drone, and tiger have in common? You want to put the common or shared stuff in class enemy so that all three of these classes can inherit from it. As far as the variables go, all enemies need to have an X position, Y position, and health variable. Declare them once in parent enemy, and all child classes, soldier, vampire, drone, etc., will have these properties, will have these variables. What about methods? All enemy objects need a move method and attack method. Enemy move about the screen and launch attacks at the player. Functions or methods define what the object does. What do all these objects have in common? What do they do in common? Those are the methods you want to put in class enemy. When designing a parent class, put all the shared variables and methods for all the child classes into the parent. Everything that they have in common belongs in the parent class. Class soldier. Unique or specific elements in the child class soldier. What properties or methods only a soldier needs? When you're designing the child classes, you've got to think about, well, how is this different from the other classes? As far as the variables go, only a soldier needs a rank and weapon variable. Is the soldier a private or a sergeant? Does it have a handgun or a rifle? Tiger and drone don't need these variables, but soldier does, so declare these specific or unique variables in class soldier. What about methods? Only a soldier needs a reload method. Since tigers don't change their claws and drones can't add new missiles in flight, reload is something unique to a soldier variable, so a reload method belongs in the soldier class. When designing a child class, put in the unique variables and methods for just that child class. If it's something everybody shares, it belongs in the enemy class. If it's something specific to a soldier, it belongs in the soldier class. Designing the drone child class. Unique or specific elements in the child class drone. What variables and methods does only a drone need? As far as variables, flying. A drone is the only thing on this list that can fly. Any property like height or altitude or airspeed that has to do with flight should be in the child class drone. Methods. Only a drone needs a remote command method. A drone has someone on the ground sending remote commands like lower your altitude. Anything about the remote control of a drone belongs in the child class drone. Put the common or shared elements in the parent. Add unique or specific elements like flight in the child class. Design a child class tiger. Unique or specific elements in the child class tiger. What properties or methods does only a tiger need? As far as the variables go, an is-kitten Boolean variable. When it's true, it meows instead of roars. No such thing as a baby drone, but a baby tiger is the cutest thing ever. Declare this variable in the child class tiger. What about methods? Only a tiger needs a slash and or bite method, especially out of this list. And with the is-kitten variable, you can laugh when a baby tiger bites and, die when an adult tiger bites. A class vampire and a class tiger both might have a bite method, but they're very different bites. Add unique copy of each in the child class. Inheritance is most often used when designing multiple related classes. Write the common code once and share it with the child classes. Soldier, drone, and tiger are all things that are going to attack the player character during a video game. Enemy is the parent class, so the child class, vampire, mutant, soldier, tiger, etc. Car would be the parent class, so the child classes Ferrari, Corvette, Prius, Tesla. Shape would be the parent class, so the child class circle, rectangle, and triangle. Do you see where we use inheritance? I am going to design a set of classes that have things in common. Soldier, drone, and tiger are all things that will attack the player character during my game. Therefore, I'll use inheritance to take advantage that they have a bunch of stuff in common. I'll write it once in class enemy and not have to repeat it in the child classes. If I was creating a car racing game, I'd be creating very many different car objects. Rather than write all the code in every single object, I'll use inheritance. I'll build a car parent class and then create subclasses out of that. Therefore, everything these things have in common could go in the car class once, and I only have to add the unique elements into Corvette or Prius or Tesla. Shape is the parent class to child class circles and rectangles. Circles, rectangles, and triangles have a lot of things in common, so I'll put it in the shape parent class, write it only once, and inherit it in all the child classes so I don't have to repeat that code. More code in the parent class equals faster development, plus it adds code reuse. That's why we use inheritance when designing related classes. They can take advantage of the code reuse. Write once in the parent class and use it over and over again in the child classes. Let's see it in action. Create a soldier object equals soldier. That'll build me in memory a soldier object, and I'll assign a reference to soldier object. Notice how the variables are from soldier are in blue and from enemy are in red. The soldier object contains the variables we created in class soldier and the methods we created in class soldier. Those are in blue. But soldier inherits from enemy, and enemy is in red here, and all the variables we inherit from enemy, like xpos, ypos, and health, are in red, and they are part of the soldier object. And the methods we built in the enemy class, move and attack, they're in red. Those are all inherited from the parent class enemy. An object is a combination of variables and methods from the parent and the child. Drone object equals drone. Notice how the drone object has its own variables and methods like airspeed and height, that's in blue, and remote command, that's in blue. And it has variables and methods from the parent class, xpos, ypos, health. All of that was inherited from enemy. The methods move and attack, inherited from enemy. We put the ones that the child class created in blue and the ones inherited from the parent class in red. Tiger object equals tiger. We'll build a tiger object with everything it has and assign the result to the tiger object reference variable. Note the enemy variables and methods in red only have to be coded once in the parent class. That's the advantage of inheritance. There is lots of stuff that these things have in common. I put that in the enemy class one time, and all these subclasses pick it up automatically. It's the same code used in all three objects. This is code reuse. This means I can write my subclasses much faster because they're picking up so much inherited code. Make sure in the superclass you place all the common or shared variables and methods. Think about what soldier, drone, and tiger have in common, and that's what belongs in class enemy. In the subclass, place all the unique or specific variables and methods. What is specific to a tiger? Those are the variables and methods that belong in the tiger class. Follow those two simple ideas. Common or shared goes in the parent class. Unique or specific goes in the child class, and you will be a good object-oriented programmer. Private, public, protected. I really struggle with this slide. Half the Python documentation online refers to these as hidden variables versus non-hidden variables. And the other half of the documentation online refers to private variables versus public variables. I guess it boils down to what programming language you used first. Private, public, and protected variables have existed for a long time in languages like C++, PHP, and Java. Everybody in those languages tends to refer to these things as private, public, and protected. Python's creators started calling these hidden and non-hidden variables. So again, some of the documentation says hidden, non-hidden. Some of the documentation says private or public. I'll try and use both terms as we go through this slide. Private, public, and protected are access modes. What code has direct access to this element? When something is private or hidden in Python terminology, only this class has access to the element, aka hidden. It must start with a double underscore, and every variable that starts with a double underscore is considered private or hidden variable. Public variables. All code has access to this element. When something is created as public, you're saying I want everyone to have access to it. Without any underscores in front of ypos, then this is a public variable. It's not hidden, and everybody can change the value of the ypos variable. There's a new mode called protected. This class and child class should have access to the protected variables. Protected is defined by a single underscore in front of the variable name. Does that make clear? It's private when there's two underscores. It's public when there's no underscores. And it's protected when there's one and only one underscore. The variable underscore underscore xpos is created as a private or hidden variable because it starts with two underscores. That means only the class enemy has direct access to underscore underscore xpos. The big red box right here indicates the code with direct access to this variable. The arrow points to where that access is being set to, private or hidden. It's the double underscore that makes it private or hidden. There it is right there. That means I cannot access this variable down here, and I cannot access this variable outside the class. The class Tiger inherits the underscore underscore xpos variable. Because it's private though, Tiger does not have permission to access underscore underscore xpos. It is not able to assign a new value. This is something you cannot do in the subclass. You cannot go up to the x position variable, even though Tiger inherits it, even though it's part of the Tiger object, you cannot directly change the value of xpos. If enemy had a setter method, it could be called to change underscore underscore xpos. There is a super command, which we'll look at very closely, that says go run the set xpos method that I just inherited, set it to 30, and that would change this variable. But without a set method, you do not have the ability to change xpos. Even though it's private, you still have to understand that Tiger still inherits the variable. Tiger inherits every variable up here, whether it's hidden or not hidden. And of course, if xpos is a hidden variable, I certainly cannot use a Tiger object to change it. Since the variable underscore underscore xpos has been created as a private or hidden, the class Tiger inherits it, but Tiger objects do not have permission to access this variable. Underscore underscore xpos is off limits to Tiger objects, and it cannot directly assign a new value. If enemy has a setter method, it could be called to change xpos. So for instance, I cannot do this, directly change the variable, but if there was a set method to let me change the variable, I could call the set method using a Tiger object, and it could go ahead and change the variable for me. This is important to do it this way because set methods can guarantee good values for the private or hidden underscore underscore xpos variable. One of the big advantages of hidden variables and using set methods is you can protect from bad values being assigned to your variable. X position might have a fixed set range between 0 and 100, and any value outside that range is bad. If you force the user to call a set method, you can verify that the value passed to be set to the object variable is good. The variable ypos has been created public. Class enemy, class Tiger, and all classes have access to ypos. The big red boxes indicate the code with direct access to the variable ypos. In other words, all the code has access to ypos. The arrows are where the access is used to change the variable. You can see I change it in class enemy, I change it in class Tiger, and of course I change it outside the class because it's public or non-hidden. Anybody, anywhere that has a Tiger object can go ahead and change the value of ypos. But this can be a problem. The problem with creating public variables, any changes to the variable ypos means you may have to change everywhere the variable is used. If somehow, someplace I change this variable, either change the name of the variable or change the type of the variable, then I have to look through the entire code wherever I use it and maybe change that code too. What's the other problem? Because it's public or not hidden, it means there's no way to prevent garbage in, garbage out. If somebody wanted to set TigerObject.ypos to negative 487,265, there's nothing you can do to stop them. This may be an absolutely bogus value for this variable, but there's nothing you can do to stop it from happening. If you force users to call set methods to change your variables, you could say, I reject this value. I will not change ypos to this bogus value. The variable underscore health has been created in protected mode. The class enemy and any child class, including Tiger, do have direct access to underscore health. The big red box indicates the code with direct access to the variable underscore health. The arrows point to where that access is used to change the variable. With a single underscore, of course, enemy can change its own variable. The single underscore also tells the child class that they should feel free to change this variable. However, in Python, this is on the honor system. Python does not enforce this restriction. Other computer languages are much more strict about protected variables, but Python says this underscore is just a signal that maybe you shouldn't directly change the value of this health variable. The variable underscore health has been created protected. Class Tiger inherits enemy and inherits the underscore health variable. Because it is protected, Tiger objects should not directly assign a new value to underscore health. Protected is closer to public than private because it's on the honor system. Again, I'm not sure why Python even bothered with this. If it's just on the honor system and anybody who wants to do it can do it, I don't see how it works, but I guess they wanted to be like other languages. All the underscore does is warn the programmer they should not directly change the variable. They're hoping by putting an underscore in front of the variable, you won't do this. But I'll be honest with you, there's nothing that stops you from doing it. The protected access mode is kind of silly. The single underscore is just a signal, please don't change the underscore health variable directly. But there's nothing that prevents it. Double underscore enforces it and says, no, you cannot change this variable directly. You must call a set method. With the caveat that there are always exceptions to any rule. Create your variables in init as private or hidden. Then write get and set methods with public access. When doing inheritance, try to use protected mode to suggest direct access to all child and subclasses, but keep in mind, it does not protect the variable like private or hidden does. Let's trace the code and see how this works. I also want to introduce you to the super function that allows you to go up to the parent class and see how that works. Tiger object equals new Tiger. Let's execute the Tiger constructor. As with all constructors, as soon as we call it, self will be set to Tiger object. I want the self variable to point to the same object as the Tiger object. Here's the object down here, and Tiger object is a reference to this Tiger object. The super function says run the parent constructor init. We may also use super to run other parent methods. Remember, Tiger inherits everything that enemy has. When you use super, you're saying go to the class that I inherited from, enemy, and run something in enemy. So this line of code says jump up to my parent class and run init in my parent class. Also notice that self is now pointing to the same object as Tiger object. Now executing in the parent class, self._exposition equals a 20. The enemy constructor sets the default values for the object variables, and a 20 appears in the object itself. Self.ypos equals 40. The 40 gets assigned to my variable, my object variable. That's what init does. It initializes the variable. Self_health equals 100, and follow the arrow. You can see 100 appears in my object. Remember, Tiger did not create these variables. Why not have the parent class initialize the variables for you, and Tiger will inherit those values? Before I leave, notice that this is the last line of the method. Here's my indented code. I'll execute all the indented code. When I stop indenting, the function or method is done. When this guy returns, it will return to the line of code after the call to super. It returns to the calling function. After returning from super init, the Tiger constructor can change the values for the variables and properties if it wants. This is entirely optional. But if Tiger wants to change Y position to 10, Tiger can change Y position to 10. The Tiger constructor can change the values of the variables and properties if it wants to, and each child class can set their own unique value. That's what child classes do. They make themselves different than the parent class. So Tiger decided it would rather have a 10 in this variable, and it changed the value of that variable. Tiger also decided it wanted a different health value, so Tiger changed the health value to 90. The child class can customize whatever it wants from whatever it inherited from the parent class. Also, keep in mind, this is the last line of code in this constructor. Notice how the indentation changes? That's the end of this init function. What happens when you finish a function? It returns back to whoever called you. Returning back, the Tiger object is completely built. Now, I only did this to demonstrate how an object can change a public variable. I prefer if you do not declare public variables. Keep all your variables hidden is a better programming practice. But it also shows when you're outside the class, you can use an object. We're going to use Tigger object to change the Y position variable. Notice how outside the class, I use the Tigger object to follow this reference and go inside here and change it. Notice how inside the class, I use the self variable. And that's because at the time this executed, self was pointing to the same object. Again, I have to apologize for one thing. Half the Python documentation calls this hidden and non-hidden variables. The other half of the Python documentation calls this private and public variable. However, I decided to keep with private, public, and protected to reinforce that terminology and prepare you for if you go on to other computer languages like C++ or Java, we'll use the terms private and public. Python, keep in mind it's the same as hidden and non-hidden. Polymorphism. Poly means many. Morphism, to change shape or form. Polymorphism is the ability of an object reference to change, to morph to another object type. Polymorphism is a common sci-fi movie or TV special effect when something morphs or is a shapeshifter. The Star Trek series has a lot of shapeshifters in it. The Harry Potter movies had magic spells and potions that cause shapeshifting. Shapeshifting is something you see in science fiction movies or Harry Potter. In OOP, polymorphism requires understanding inheritance. It's very important to understand that polymorphism requires doing inheritance. Soldier inherits and drone inherits, Tiger inherits. Soldier, drone, and Tiger all inherit enemy variables and methods, and that is a necessary element to do polymorphism. When a soldier object is created, it will have all the enemy variables and methods. That's inheritance. Soldier object equals new soldier. Soldier object is a reference to this soldier object, and you can see the soldier variables and methods are in there, but the inherited enemy variables and methods are also in that same object. Drone object equals drone. Drone object is a reference to this drone object, and of course it has drone variables and drone methods. But drone inherits from enemy, so you get enemy variables and enemy. Tigger object equals Tiger. Tigger object is a reference to this Tiger object. When a Tiger object is created, it will have all the enemy variables and methods. Note all three objects have the same enemy variables and methods. Here is the enemy variables and methods in Tiger. Here they are in drone. Here they are in soldier. That's a key element to doing polymorphism. You need to have a bunch of methods with the same name. You need to have a bunch of inherited methods that all the objects will share. Create an enemy object reference variable. A reference that has not been assigned an object contains a reference to none. I'm going to create this as sort of an empty reference for now. The empty reference will point to none, so I'll put a none in that variable. As of this point, enemy object is not pointing to a specific type of object. However, let's assign a soldier object to the enemy reference variable. Why not? It has all the enemy's variables, and it has all the enemy's methods. It looks like a duck, walks like a duck, and quacks like a duck. It's a duck. A soldier object is an enemy object. If I follow this line and follow enemy object down into the soldier, notice what you see inside the soldier object: enemy variables and enemy methods. A soldier object is also an enemy object at the same time. Let's assign a drone object to the same enemy reference variable. That's the morph. Did you see it? The enemy object reference was pointing to a soldier, and it changed over to a drone object. Enemy object equals drone object took the reference that was pointing over here and moved it over to this object. Well, why is that important? Enemy object just morphed. It morphed from being a soldier to a drone. Assign a tiger object to the same enemy reference variable. This is polymorphism, many changes. An enemy object reference went from a soldier to a drone to a tiger object. See this line of code, enemy object equals tiger object? It took the line that was pointing to the drone object and morphed it over to the tiger object. Do you see the polymorphism? We started over here, we morphed to a drone, we morphed to a tiger. That's polymorphism. There's a reason why I drew enemy object in red. It can refer to any object that has enemy variables and methods. If we had zombies, vampires, mutants that all inherited enemy object would work for those too. I drew the variables and methods in red so you highlight them and see that all of these objects have this stuff in common. And there could be plenty of other objects that have this stuff in common. And any one of them could be assigned to this enemy object variable. One thing I want to make very, very, very clear. The objects themselves do not morph. This soldier did not morph into a drone. It stayed a soldier. What morphed was this reference variable. It started here, then it morphed to here, then it morphed over to there. It's the reference variable that morphs, not the individual object. And just to be clear about it, let's morph the enemy reference variable back to a soldier. A true polymorph can go back and forth. It looks like a duck, walks like a duck, and quacks like a duck. It's a duck. If this object has all the enemy's variables and all the enemy's methods, then it's an enemy object. This last line of code was sort of complete the circle. A true polymorph should be able to go back and forth. And it went from a soldier to a drone to a tiger and then back to a soldier. Why polymorphism? Instead of the same enemy every time, we could use different opponents. We can mix it up. Our code on the first level doesn't always have to fight a soldier. We could randomly pick at the start of the level, I want to fight a random enemy. And if the random number generator says this is a soldier, then on level 1 you'll fight a soldier. If the random number generator says this should be a drone, then you'll be fighting a drone. If the random number generator says you'll be fighting a tiger on this level, then you'll fight a tiger. Polymorphism provides a way so that you can really mix up how your game plays. A super important key to understanding polymorphism. Methods with the same name is super important. When you inherit from a parent class, you get a set of methods like move and attack that every object inherits. Since every object inherits, you don't have to worry about what type of object it is to run those methods. It's extremely important for polymorphism when you're designing your child classes that the child classes have a set of methods with the same name. Last slide, I promise. Polymorphic lists. What is that? Polymorphic list. Remember, poly means many, and morphism means to change shape or form. A classic use of polymorphism is drawing the screen. Next time you play a video game, look closely at the background. It's composed of many circles, rectangles, and other shapes. Think of tiles of different shapes and colors. Arrange them to form a picture. An artist would call that a mosaic, and it is how games generate a virtual world out of thousands of shapes. When you walk into a room in a video game, you're not looking at a rendering of a room. You're looking at hundreds, if not thousands, of tiny little shapes. And when the artist has arranged them, the room appears. So let's create a class circle that inherits shape. Let's create a class rectangle that inherits shape. Let's create a triangle that inherits shape. Here's the inheritance diagram over here. Circle, rectangle, and triangle all inherit shape variables and methods. That's what inheritance says. Everything that shape has, circle, rectangle, and triangle will inherit. Polymorphic list. Let's start with an empty list of 5 shape objects. Polymorphism means any class that inherits shape can be stored in this list. Circle, rectangle, triangle. All of those shape objects can be stored in our list. Screen equals square bracket none into square bracket times 5. I want to create a list holding the value none. Times 5 means I want 5 slots. And there you see it. I have 5 slots in my list, all referencing the value none. Since circle inherits all of shape's variables and methods, let's assign a circle object to a shape list element. That's legitimate. Thanks, inheritance. Circle inherits everything that shape has, so I'll take a circle object and put it in my shape list. And you can see slot 0 or index 0 of the screen list contains a circle. Since rectangle inherits all of shape's variables and all of shape's methods, assigning a rectangle object to the shape list element is legitimate. If it looks like a duck, walks like a duck, and quacks like a duck, it's a duck. This is definitely a shape object, so assign it to my shape list. And even though it's different than a circle, it has all the shape's variables and all the shape's method. In index or subscript 1 of my list, I'm going to insert a rectangle object, and you can see this reference goes back to slot 1 or index 1 of my list. A triangle has all of shape's variables and all of shape's methods. It's a shape object and can be assigned to a shape list. Screen square bracket 2 and a square bracket says go to reference index 2 and assign a triangle object to that, and there's our triangle object, and it is in reference 2 of our list. This is a polymorphic list. I can fill the list with all triangles, I can fill it with all circles, or I can mix and match it to any way I want. Filling the list with additional objects, any object from a class that extends shape can be assigned to any slot in the list. Remember, lists are also known as arrays. In Java or C++, this would probably be an array. In Python, it's a list. The list is a close equivalent to an array in another computer language. The thing that's different about a list is it's much more dynamic. The list could be filled with 5 rectangle objects or 3 triangles and 2 circles. For example, if I was building a brick wall, it could be created by storing many rectangle objects in the list, not just 5. Brick walls are a famous example of building a screen out of multiple small shapes. So screen 4 or subscript 4 will get a triangle object, and what I've done is I've filled my screen list with a variety of different objects. Polymorphism says one reference can point to many different things, and I'm taking advantage of that by saying one list element could point to a circle or a rectangle or a triangle. That's polymorphism. Let's write some code that takes advantage of this. What can we do with a list of shape? If each shape object has a draw method, and a simple for loop spins through each slot of the list to call that draw method, we could write a simple piece of code that draws hundreds if not thousands of shapes on the screen. Here's a form of the for loop for each item in the screen. Go to my list and set each item to each element in my list. The first time through, I'm going to set each item to the first element in the list, or slot 0 of my list. Each item is definitely part of the list, so this will return a true statement, and I'll go inside and execute the code inside the loop. At the time this executes, each item is pointing to slot 0 of my list. Access the object at index 0, or each item of the list, and execute its draw method. So I'll go to each item, the dot says go inside the object, run the draw method, and it draws a circle on the screen. If I'm a circle object in slot 0, if each item is pointing to a circle object, the circle object will draw a circle. Looping back up, bump to the next each item in the screen list. Each item just moved over to slot 1 of the list. Each item is definitely still in the list. You can still see it's pointing to an object. So each item in the screen list is a true statement. I will go inside the code and execute the draw. Access the object at index 1 / each item in the list and execute its draw method. Look at this code carefully. It says start with the each item reference. The dot says go inside this object and execute a draw. Well, what will the draw method do inside of a rectangle? It'll draw a rectangle. That's what it do. Hit the end of the for loop and bump to the next each item in the screen list. Look what happened to this variable. It went from this object over to that object. That's polymorphism. So now each item is pointing to this triangle object. Is each item still in the screen list? That's a true statement. Each item is still a valid reference to something in the list. So I'll go inside the loop and execute the draw. Access the object at index 2 / each item of the list and execute its draw method. Each item is a reference to this triangle. So when I get to the triangle and say draw, what do you think a triangle object is going to draw? That's right, it's going to draw a triangle. Hit the end of the for loop, bump back up, and set each item to the next item in the list. And you can see each item, like a true polymorph, is morphing between the different types. It started as a circle, then it morphed to a rectangle, then it morphed to a triangle, and now it has morphed to a circle again. Each item is definitely still in the list, so this is a true statement. We're still in the list. Go execute the draw. Access the object at index 3, which each item is pointing to, of the list and execute its draw method. Start with the each item variable. The dot says go inside of it. And if I'm inside a circle object, what do you think it's going to draw? That's right, another circle. Hit the end of the list, bump to the next each item in the screen list. Is each item still in the screen list? That is a true statement. Each item is still pointing to a valid object in the list. So that's a true statement. I'm going to go in and execute the draw once again. Access the object at index 4, the same one that each item is pointing to of the list, and execute its draw method. Go to the each item variable. There it is. The dot says go inside this object. Well, that's a triangle. What do you think a triangle object is going to draw? That's right, another triangle on the screen. Bump to the next each item on the screen list. However, I've ran out of things in the list. What is each item going to point to? Frankly, I'm not sure what each item is going to point to. But when I get back up to the for loop, each item in the screen list is now a false statement. I've run out of objects in the list, so this will return a false. Clearly, each item has reached the end of the screen list, and the loop evaluates the false. And when the loop evaluates the false, it leaves the for loop. So now we know two things. Number one, I'm a terrible artist. What is that? Some sort of demon jack-o'-lantern? I don't know. And I drew it. Number two, simple code can draw many different numbers and types of shapes on the screen to create a virtual video game world. And the only thing we really need is methods with the same name. It's very, very important for this example that each one of these objects has a draw method that draws itself on the screen. Once you build your objects with a set of methods with the same name, you no longer care what each item is pointing to. You just call the common methods and boom, they execute. This can greatly simplify our code, and we can write very, very powerful draw routines that take very little code. The best thing about object-oriented programming is once you get good at it, your code becomes very, very simple. 2 lines of code to draw an entire virtual world. Whether this was a Donkey Kong style game where you're drawing anvils and ladders and barrels on the screen, or you're doing a 3-dimensional world in a first-person shooter, this same piece of code can draw any screen that you want, as long as all the objects share certain methods like draw.